Now with round 2, take it away, Steve.
Okay. Aleksander, are you here? Aleksander Mądry? Because I'm not sure I'm going to need the whole second hour, so if I run out of gas, maybe Aleksander can get started early, or else we can have an early break and then he can have a slightly longer last session.
Nothing wrong with early breaks.
All right. Okay, so Michelle actually pointed out at the break that this picture isn't completely accurate, so maybe I'll eat up some time trying to correct it. And the reason is that on the predictor steps, when you're starting from inside here, you're actually tangentially heading right for the origin. And so they're going to start out heading that way, and then of course they're going to like veer away and run into the outer boundary. And so a more correct picture would look something like this. There's the central path. Here's the outer boundary. Here's the inner one. So I guess you would start here, and then you would start out heading for the origin, but get stuck and get stuck at a point here, and then the corrector step would take you back inside. Okay, and then you'd sort of repeat that process. So that's probably, yeah.
The corrected direction is actually a line, right? It's constant co-centering direction.
So it's going back towards the middle. So is that, it's actually a line?
Summation, mu stays constant, right? Summation of xi si's stay constant.
Yeah, the summation stays constant, but the actual pairwise products might be still quadratics, aren't they? Or
there are some stays the constant.
I see, but they
so
somehow cancel out.
Yeah, exactly. You're like 45 degrees, right?
I see. So you think it's more like that?
Right.
Okay. Heading back for the. Okay. Good. So I'm learning a lot here. So. Okay. Thank you. All right. So here's another approach that was also very popular back in the 90s, sort of as an alternative to this explicit path following approach where you're trying to keep all the xi-si products in balance. You can also do that implicitly through the use of a formula. And of course, barrier methods draw their motivation originally from the log barrier idea, as I'll talk about presently when I just talk about primal barrier. And so naturally people were sort of thinking about how to extend this into this log barrier idea into Primal-Dual space. And here's maybe the most successful way of doing that. You can define this function phi of rho, which is dependent on xi-si products again, and it involves logs, and it involves this parameter rho. And you can define it like this: log of x transpose s minus the sum of the logs of the individual pairwise products, xi-si, where rho is something greater than n. Now, by messing around with this a little bit, by adding and subtracting n times log mu to the first terms and the second term, actually subtracting it from both terms, you can rewrite that expression like this. So modulo this constant, you'll see there are two terms here, and this one sort of penalizes it where the xi-si is much smaller than mu. So if one of the xi-si's is much smaller than the average, this is going to be a tiny number close to 0, which means its negative log is going to be a big number. So you're going to pay a penalty for that. So, and then the first term, of course, is because rho is greater than n, this is something that you're going to want to drive to minus infinity, okay, because you want to drive mu to 0. So again, you see this balance between trying to stay central by keeping the xi-si's close to mu, but at the same time trying to drive the mu to minus infinity, okay? So it's got the same kind of motivation as we've been talking about already. So, okay, so again, you maintain strict feasibility of all the iterates because you want these xi-si pairwise products to be strictly positive so that they're in the domain of the log. Once again, you take these modified search directions based on that parameterized algebraic system, f of sigma times mu, where you choose the sigma here to be n over rho, okay, based on the barrier parameter rho. And at least in the classical methods, you do a line search along this Newton direction in such a way as to minimize the barrier function. Okay, and you pick the alpha that minimizes the barrier function along that direction. So the complete algorithm looks a lot like the ones that I've already defined on previous slides, in that you just have a series of iterations, you stay strictly feasible, you pick the parameter rho up front, you choose the deltas to be the Newton step for f of sigma times mu, where sigma is just n over rho. you take the longest step that you can take while staying strictly feasible, but you try to minimize the barrier function. So that will actually kind of guarantee that you stay strictly feasible. And then you just take that step. So it's really just the same sort of search direction, the same sort of line search, but just using a different criterion to choose how far you go along that direction. So what can you show about this? Well, the classical results about this are as if rho is greater than n plus the square root of n, you can show that you can get at least this much reduction in the barrier function at every iteration. A reduction of at least 0.15. And what that means is that you can therefore drive the barrier function to minus infinity at this nice steady rate. You can also show that you've got this relationship that actually falls out of this expression here. You can show that you can show that the mu is bounded by the exponential of the barrier function divided by rho minus n. And therefore, by driving this to minus infinity, you're going to be marching this steadily, sort of at a linear rate towards 0. Mu is going to go to 0. So you end up with this sort of complexity, the initial value of the barrier parameter plus rho minus n times log epsilon over delta. What is delta here? I think the delta is just the 0.15. Levent, yeah. I'm looking to Levent for confirmation. All right, very good. Okay, and notice this is only true for rho greater than n plus square root of n. So you can't make this any less than square root of n. Okay, you're still stuck with a square root of n here. Okay, which as far as I know is kind of the best you can do for these kinds of methods. Okay, so back to this question of initialization, which Daniel raised early on. Okay, so...
Another question?
Yes, another question, yeah.
So, does it make sense to build a barrier where you multiply each log term by xi, si divided by mu, then you actually have a generalized entropy term?
I guess it would look like that, wouldn't it?
So,
If you mashed all these together.
so mu is basically, no, you don't mash them, but every log term inside the sum, you multiply by the formula by xi, si divided by mu, right?
So you want to scale all these individually, all these xi, si's.
So, can I just
Yeah.
I think it has a similar function. So the role of entropy is typically to even out stuff. So a log already does that. It's known in economics as disproportionally fair. Utilities that also works towards equalizing the individual terms. So in terms of what it functionally does, it should be similar.
Well, no, I haven't thought about this question, but I mean, that would correspond to some kind of rescaling of the whole LP, right? If you rescale the rows and columns of A, that corresponds to applying some sort of scaling to the elements of X and S. And are you talking about having some sort of adaptiveness of the way that you...
It's more like entropy Shannon.
Just putting an xi, si also outside.
Oh, I see, having it in front here. Yeah, I see what you mean. I don't know if that's been studied. Levent?
Mike Todd and I studied it about 20 years ago.
Okay. Very good.
It's very interesting, yeah. But I have a more recent paper. I can talk to you about this. It corresponds to a nonlinear reparameterization of that last equation, xs equals mu I. If you take logs of both sides component-wise, and then do the Newton direction, that's exactly corresponds to the potential function.
Interesting. All right. I'm sorry I'm not repeating all this for the record because it's
the natural thing to do.
yeah, that's okay. Thanks a lot for that input. Alrighty. So okay, the question of initialization. So it is non-trivial in general to find an initial point that's within this neighborhood and doesn't have an enormous value of mu naught. Okay. So there are two things you can do to fix this up. One is you can modify the algorithm so that it doesn't require an initial point. In other words, it doesn't require you to satisfy these two conditions up front. And this leads to this whole area called infeasible interior-point methods, which I'll say a little bit about. So it's sort of a generalization of what we've been talking about in a sense. And the second approach is that you can take the original LP formulation and come up with a slightly expanded formulation where the feasible point is obvious, where it's absolutely clear and obvious how to get a starting point. And this is a so-called homogeneous self-dual idea. And then you can just go and solve those. Actually, you need a slightly more general tool for solving them. you need an interior point method for monotone and linear complementarity, which I'll talk about subsequently as well. All right, so these are two approaches. I'll say a little bit about both of them. I would say in implementations that it's the first one that's implemented most often. I do know about implementations of homogeneous self-dual, but the code that I worked on 20 years ago and the other ones that I know about tend to use this formulation more. The complexity gets worse. The results for this have an order n squared in them rather than an n. But of course, as always, we seem to see an inverse relationship between worst case complexity and practicality. That's been my experience in this space. Okay.
Steve, so when you said,
Yeah.
never mind, you're going to do it.
Yeah.
I was going to ask what you meant.
All right. Yeah. Here we go. So for infeasible interior point methods, all you need is a point where the x0 and s0 is strictly positive, and we all know how to do that, right? So you can just start from the vector of ones or something. So you need to define these initial residuals, and so when you're doing the Newton equations, you no longer have zeros here on the right-hand side. You have to correct for the fact that you've got errors here. But because these two equations are linear, what happens to those terms is nice and predictable, okay? There's no nonlinearity in these first two rows. And so these things march steadily towards zero. They're all scaled by 1 minus alpha at every step. If you ever take a full Newton step, you immediately get feasible in those first two components, and you stay feasible thereafter, okay? But you give up a bit. You give up the fact that we've got delta x times delta s equals 0, and that came into that analysis of how long a step can you take. The analysis that I did in those 5 easy steps kind of depended on having this relationship, and that's no longer true. And so you have to generalize somewhat. The analysis does get somewhat messier.
And you also don't have the duality gap to play with at all, right?
You actually use the duality gap. That still shows up. You still make use of the mu. In fact, you define this slightly generalized version of the n minus infinity neighborhood, and it looks exactly the same as it did before, except it's got this extra condition in it. So again, you have, here it is here. Again, you want xi si to be greater than gamma, but you put in this extra condition that the residual at the current point, that is the infeasibility in those two linear equalities, is bounded by this multiple of mu, which is the current value of the duality gap.
So you somehow keep xi and si always positive, but
Yes.
you don't satisfy the
No,
feasibility. So you keep feasibility on that side, but not on
the feasibility gets squeezed to 0 as the mu goes to 0. Okay? So this is a way of controlling the feasibility in terms of the mu. So you have this slightly more complex definition of the neighborhood, which means that there are more conditions to check when you're deciding how long a step you can take, but they're still elementary, they're still easy to check.
question.
Yeah.
So what happens if there is no feasible solution?
Yeah, good question. Then this is going to get stuck. It's going to get stuck. It's not going to be possible to drive these to 0 and simultaneously maintain non-negativity. So the theory depends on having a feasible solution. Yeah.
But do you get a certificate?
No, you don't with this method. There are actually modifications where you do. Yeah, I take that back. Yeah. I'd probably even
You
put
have to
that.
work harder on this version, but it
Yeah.
seems easier on the homogeneous self-dual embedding than
Yeah.
this. But you can
Yeah, I
also
think-
get some certificates from
I think there are guarantees that you can show that if there's a solution whose norm is less than a certain quantity or something, then it's guaranteed to find it. I think, yeah, that's even in some of my papers. Okay, but yeah, it's homogeneous self-dual has a much kind of more elegant theory as far as giving you certificates of infeasibility, which I'll talk about in a moment. All right, I'm not going to go into a lot of details in this because the spirit of the analysis kind of tracks what I did so far. It just all gets kind of messier because of the need to deal with the residuals as well. But in the end, you're able to show that the steps that you can take are greater than some multiple of 1 over n squared, and that leads to this order n squared log epsilon type iteration complexity. Okay, now before I talk about homogeneous self-dual, I need to tell you about the extension to LCP, monotone and linear complementarity. So this is not an optimization problem. It's a math programming problem, but it's not an optimization problem because there's no objective. There's just a bunch of conditions you need to satisfy. And they look kind of familiar to you because I've already showed you KKT. So here the problem is you're looking for two vectors x and s. They're both of length n. You've got a matrix n by n. It's positive semi-definite, not necessarily symmetric. And x and s are related in this way. S is just m times x plus q. X and s are both non-negative, and they have to be complementary. So you're just looking for two vectors x and s that satisfy these conditions. Okay. Now, there are generalizations of this problem where you can add in extra unconstrained variables and not required to be non-negative, and an equal number of equality constraints. So you get mixed monotone LCPs, which have these extra ingredients. But if ever you derive algorithms for this problem, it's very easy to extend them to the mixed problem. Okay? So, in fact, KKT conditions are kind of a special case of a mixed monotone LCP. These are exactly the conditions I wrote on the second or third slide, where I had x and z and s. I had these equality conditions that were just the primal and dual feasibility. I had non-negativity, and I had complementarity. So this is just the KKT conditions written in a form that looks like this. Okay?
There, M is not PSD, right?
Yes, it is.
Sorry, Steve has a funny definition of PSD.
Okay, just checking.
If you take Z transpose this matrix times Z, you get 0.
Okay.
Every time, right? This is a homework assignment. I think that's true.
It is true.
Yeah.
But most of the time when people see positive semi-definite, they assume symmetric.
Yeah, it's not symmetric. Yeah, definitely not symmetric. Okay. Okay, so LP is really kind of a special case of this, and QP is too. If I just take the LP and put in an extra quadratic term with a positive semi-definite Hessian, the Q is symmetric here in this case, then I can write down the KKT conditions for this to be this. In fact, they're exactly the same as the LP, except I replace the 0 by a Q. Okay? And again, because the Q is symmetric and positive semi-definite, this matrix is still positive semi-definite. Okay, and so again, it's a special case of an LCP. Okay, so LCP it's a great formulation to work with. In fact, a bunch of people like Ilan Adler, who was here on Monday, I don't know if he's here today, he wrote some of the early papers on interior-point for this problem, path following methods for this problem. It subsumes LP and QP, so several of the papers I wrote also use this framework. You don't lose any generality at all. So, and also it has less notation, right? Just got X and S and M and Q, right? Instead of X, Z, S, A, B, and C. So you go from 4 objects down to, no, you go from 6 objects down to 4, okay? Bonus. All right, and the methods are almost the same. You know, the path following ideas, the log barrier ideas, they're all pretty much the same. The analysis is a little bit different because you don't have this delta x transpose delta s equals 0. Instead, it's greater than or equal to 0. So in that sense, it's the analysis is a little bit different. But basically, the complexity results are the same, and the convergence analysis looks much the same.
What's a non-monotone LCP?
That's where the M is not positive semi-definite. And they crop up a lot, like in certain game theory applications. There are certain games that have non-monotone LCPs. They're much harder to solve.
And here, do you still have the same thing that you can at some point, like, round to an exact solution?
If everything's rational.
Yeah.
Yeah, I guess so. I mean, ultimately, you're going to get. There's the same concept of a basis, right? Where at any solution, you can divide the X and S into a basic and non-basic set. And once you know that, you can get the exact solution by just solving kind of a reduced linear system here.
Yeah.
So, you know, I think the same thing is true. Yeah. Okay, so now that we've got the LCPs in the bag, I can tell you a little bit, in a hand-wavy way at least, about this homogeneous self-dual formulation. So going back to LP now, we can derive a mixed monotone LCP from the KKT conditions for LP with these very nice properties. First of all, it's easy to find a strictly feasible point for this mixed LCP. Okay, it always has a solution, And lastly, from the LCP solution, you can back out a solution, a primal-dual solution pair, to the original LP or some sort of certificate of infeasibility. So very, very appealing properties. So the idea is, again, you just go back to the original LP, give me a point x naught, z naught, s naught, with x naught, z naught strictly greater than 0. Okay, so give me that starting point. Then I'm going to define these objects. I'm going to define a B bar, which is sort of the initial infeasibility of this point. I'm going to define a C bar, which is the dual infeasibility of this point that you've given me. And I'm going to define a T bar, which is sort of a duality gap with a +1 added on. Okay, again, from this initial point. So given those objects, I'm going to write down this mixed LCP, which I know at like 3:30 in the 3:25 in the afternoon is kind of an ugly thing to absorb. But if you strip out the last row and column, it looks a lot like the KKT conditions for the original LP. But I've added in some extra variables. There are a few scalar variables here, kappa and tau and theta. They're all scalars, okay? And the kappa and the tau are complementary to each other. As before, we have the x and s complementary, just like we did in the original KKT conditions. And we've bordered the original KKT conditions with this extra row and column that involve these quantities that I just told you about. Now, this is all kind of magic. I'd have to go into a lot of detail to describe exactly why this works. But let me just tell you what happens is that you can easily write down a strictly feasible point for that mixed LCP. You can set these variables, the ones you just added, all to 1, the tau and the kappa and the theta. You just define x, z, and s to be the original x naught, z naught, s naught that you gave me to start with to define this problem. And you can show that that setting of the variables will satisfy these conditions, okay? So it'll be an initial feasible point for the LCP. It will also satisfy these inequalities. It won't satisfy these complementarities. You're going to have to run the LCP interior-point method to get these complementarities to hold, okay? But you can prove some interesting results about it. First of all, you can show that there do exist strictly complementary solutions to that problem. And that follows from the fact that it's closely related to the original homogeneous self-dual linear program. The homogeneous self-dual LP is feasible and so on. So you'll just have to take this on faith. And then there are 3 results that are sort of classical results in the literature. The first one is that any solution in the mixed LCP has the theta equal to 0. The theta is one of the variables that we had to add on. So the theta equals 0 means that this last column is going to be multiplied by 0, and what's left is going to be, it's going to satisfy the original conditions for the primal and dual feasibility for the original LP. Okay, so that's the first result. The second result is that if all of the strictly complementary solutions of the mixed LCP have the kappa equals 0, so what shows up in the mixed LCP is kappa and tau as a complementary pair. So if the kappa is always the one that's 0, and the tau is strictly positive, because they're strictly complementary, then you can get a solution of the original LCP by just dividing the z and the s and the x all by the tau, which is guaranteed to be strictly positive. So if the kappa is 0, you can recover a solution, a primal and dual solution for the original LCP. Okay? If, on the other hand, if there is a strictly complementary solution for which the kappa is positive, then you get these infeasibility certificates. Okay? So if the kappa is positive, at least one of C transpose X and B transpose Z is negative. That follows from the relationship involving kappa. If I multiply out the first row here, you can show that at least one of those 2 things will need to be negative. And if the C transpose X star is negative, that means that the dual LP is infeasible. If the B transpose Z bar is positive, that means the primal LP is infeasible. So there's very powerful theory surrounding this homogeneous self-dual. I'm sorry I can't go into more detail about it, but I've at least given you the main results. Yeah.
So is that particular complementary problem the KKT conditions for some other problem, or is it this is just?
Yeah, I didn't write out what the homogeneous self-dual LP actually was, but it's a problem where these are kind of the constraints. you can write down an objective and a constraint set that kind of looks like this.
So it is. So another way to maybe derive the same KKT conditions.
Yeah.
Or sorry, the same.
You can write out an LP which is almost as big as this, and it's self-dual. It's kind of self-dual. This homogeneous is a little bit of a misnomer because there's a non-zero here.
Right.
There's one non-zero, so it's like homogeneous to within a single non-zero. But you can write down an LP with an objective that sort of looks like this. I think it's that times theta or something. Yeah. Here's my go-to guy. Okay, so it almost looks, these are almost the constraints of the LP. It's sort of self-dual, so its dual looks almost the same to within a single thing. And so when you write their KKT conditions, they sort of collapse down to this, which is almost the original constraint set. So strictly speaking, the KKT conditions of the homogeneous self-dual form are kind of twice as big as this. But you can sort of mash them all together because there's a lot of redundancy. And you end up with this. So that's why I skipped straight to talking about this. Okay, so I'm pretty much done with Primal-Dual stuff. So let me say a few words about.
What's the complexity of that one?
Well, that's the same. That's again, you can apply your favorite path following algorithm to this. Long step, short step, Primal-Dual log barrier, whatever you like, and you get those same complexity results. They're going to be related to n, where n in this case is the total dimension of this thing, but that's like 2n plus m. So it's still kind of the same n.
Wait, so just before we move on,
Yeah.
so the infeasible interior-point method, complexity n squared.
Yeah. It's the best.
This one could have complexity root n.
Yeah.
It's still the case that the infeasible interior-point method is better.
Yeah, just because there are kind of, when you implement them in practice, there are a few implementation bells and whistles that really make them work, and it's not so clear, including initialization. There's sort of heuristics for doing initialization. But I mean, there was a production code written in the mid-90s that used this form. But to my knowledge, all the codes that are out there now use more of an infeasible framework. That's to my knowledge, and I'm not totally up to date on that. MOSEC?
MOSEC is using this
It uses this? Okay, very good to know. MOSEC is a high quality code. So. Yeah, that was who I had in mind, because actually the code that Erling wrote when he was at Iowa in the mid-90s used this form. And I guess he stuck with it over the years.
Just a question, in practice, in terms of like iteration counts, does it ever go above like 50?
Yes, it does go above 50, but not a lot above 50. This is something I was talking to Ron Graham about at the break, actually, that in practice you don't really see much dependence on n. And so it was a bit of a holy grail for a while in the early 90s to try to find out if there was a method that didn't depend on n at all, just had a constant bound or a log epsilon bound. And as far as I know, that's not the case. Yeah, but in practice it seems to be sort of constant. I mean, you can get nasty problems where it takes 100 iterations or something. But usually, for one of these high quality codes, it's usually more than a few dozen. And I guess I haven't talked at all about bit complexity, but operation complexity, obviously each iteration costs you order n cubed, okay? Because you just got to solve that linear system, which is size 2n plus m. So that's sort of an order n cubed operation. So if you bring that if you multiply that by the iteration complexity, you get this order n to the 3.5 log epsilon. If you want to go and talk about bit complexity, if you're assuming all the data is originally rational and it takes L bits to store, you can show that all of these operations that you do, you can sort of do them in rational arithmetic, or you can at least approximate them well enough in rational arithmetic that the storage doesn't explode. And you can show order n to the 3.5 L in bit complexity as well.
So one of the things that I think people at the beginning of interior-point methods or the barrier method didn't understand well is whether things get more singular as you get closer to the solution.
Yeah.
So do you avoid this by working on this neighborhood, in this central neighborhood of the path, or is
you can if you're going to a non-degenerate solution, then where the basis has the right number of elements and the basis matrix is invertible, then this matrix actually approaches something nice. Okay? Because if you've got the right number of xi's, I'm dealing with an m by n matrix A. If you're heading to a solution where the right number of xi's are positive, which is m, the same as number of rows in A, that means n minus m of the si's are positive. If that basis matrix is well conditioned, this whole thing is actually pretty well conditioned. Okay? What hurts you is that you normally don't solve this matrix. Normally don't solve this system in this form. You do a bit of block elimination to get it to a more compressed form, and the block eliminated form has nasty conditioning. The first thing you'd want to do is multiply the last row by x inverse and subtract it from the first row, because thereby eliminating the delta s's from the whole thing. And then that introduces an x inverse s here, and that's going to have some elements going to 0, some going to infinity. And then you can go a step further and do another step of block elimination to get an m by m system. And that has nasty conditioning. Well, it can have nasty conditioning, right? But it turns out the nastiness comes in sort of a benign way. I had a couple of papers in the late 90s, and a few other people did as well, that show that if you do a careful traditional linear algebra error analysis on this, you can show that the nastiness doesn't hurt very much. That you still get, the errors crop up in places where they don't really affect the choice of step length and so on.
If you have a strict complementary solution, or like always?
Yeah, if you got a pretty nice solution, I think you still need that.
What does a pretty nice solution mean?
So LPs are guaranteed to have strictly complementary solutions, right?
That may not, yeah, but that may not be.
Not necessarily having the right number of non-zeros, right? So, yeah.
I'm just curious. So, what is the measure of niceness that would say something about the condition number of the system you have to solve?
You would need to. Okay. I'm going to have to go back and look at my papers on this. But certainly in the non-degenerate case, everything is cool. Even when you go to the highly compressed form. In the highly compressed form, the linear system that you solve is A times S inverse X times A transpose times delta Z equals something. Okay? Something on the right-hand side. So if you've got exactly the right number of basic elements, that means at the solution you've got xi positive for I belonging to the basis, and there are exactly m of these, okay, and si is equal to 0. And then for the non-basic set it's the other way around, okay, not in the basis.
And that's for the optimal solution.
That's for the optimal solution, right? So you want to keep track of what's happening to this matrix. So this matrix S inverse X, it's the diagonal of xi over si. Okay, so for the ones belonging to the basis, these elements are going to be approaching plus infinity, right? And for the ones not in the basis, it's going to be approaching 0. Okay, so if you've got non-degeneracy, if the number of non-zeros in the basis is equal to m, then you've got m of these blowing up and the other end going to 0. So in the limit, you kind of get a weighted, weighted version of A transpose A. But, okay, what's it going to be approaching? It's going to be the basic part of A times the basic part of S inverse X basic part of S inverse X times the basic part of A transpose. All right, so if all of these are going to infinity at kind of a reasonable rate, at roughly the same rate, this is well conditioned and square. This matrix is blowing up, but all of the eigenvalues are blowing up at once. So it can actually maintain a reasonable condition number. And if you maintain the centrality, the central path neighborhood thing, these are all going to 0 at roughly the same rate. And so you can sort of show that it's not too bad.
But so if you do have degeneracy, you can't just say the same thing, but starting with the analytic center of the optimal phase.
Yeah, you can kind of say the same thing, I think. I think you can say the same thing. I'll look at my papers during the break and verify that. But I think that's true. Yeah. Okay, very good. Any more questions? We've gotten off on an interesting line of discussion.
You can give reasonable bounds on how much it changes when you take some interval over the central path. Like you can say over the central path how much multiplicatively x and s change.
Right.
Which
Right.
works when you want to do finite arithmetic, at least in theory.
Where's what?
If you want to do bounded precision, at least in theory, for then many of the places you'd use it, that.
Right. Okay. All right. Any more discussion? Okay. I'm learning a lot here. Okay. So let me just say a few words about barrier methods. So the log barrier idea goes back at least to this paper of Frisch in 1955. And the idea is whenever you've got a constraint, an algebraic constraint that you want to stay greater than or equal to 0, you just deal with that by adding a minus log of that term to the objective, weighted by some parameter. So what does that do for you? Well, if I draw a picture of what that looks like, it's pretty clear that you need the CI to be strictly positive in order for this thing to be defined at all, because a log of a negative number isn't going to work. But it's going to look like this. Okay, so this is minus log of c as a function of c. All right. So the idea is that you start off with, suppose you've got minimize f of x subject to ci of x greater than or equal to 0. You just convert that into a parameterized problem, f of x minus tau times log ci of x. Okay, and when you add in the f to this as well, the f is going to cause this thing to distort, but you might end up with something like this when you put both terms in. You might end up with something like that. So this is f plus or f minus tau log ci. Okay, so as you decrease tau, the region within which it zooms off to infinity gets squished closer and closer to the boundary. So decreasing tau means you put more and more emphasis on minimizing the f rather than steering clear of the boundary of the constraint region. And so you tend to get these contours squishing up closer and closer to the boundary as you decrease tau. Okay? And so the idea is that you start out with some modest value of tau, where you've got a nicely well-conditioned function here. You take the approximate minimum of that function, and then you decrease tau, do a Newton method or your favorite optimization method to find the minimum of the next version, okay, the next parameterized version. And you essentially just track it all the way to until tau gets small enough and you get close enough to the solution. That's the basic idea. All right, so if we apply that very simple idea to our LP formulation, primal and dual, remember in the primal formulation we just had xi greater than or equal to 0. Well, here's where I whack in the log barrier on the xi terms. Notice I've shifted the weighting term, the mu. I've just divided the whole objective by mu. So instead of having c transpose x minus mu times sum of the logs, I've got 1 over mu times c minus just 1 times the sum of the logs. I keep the linear constraints around, so I've still got ax equals b floating around here. If I go and do the same thing to the dual, then I'm doing to the dual form without the s in it, without the dual slacks. So I'm using the dual form where the constraints are a transpose e less than or equal to c. And they're the things that I'm penalizing with the log. Okay, and I've got a maximization here, so here I've got a positive log rather than a negative log. Okay, so here's the primal-dual log barrier pair, and so I can then derive a primal log barrier by just applying my favorite method to this function. It will have to be not just Newton's method, because I have to keep track of these constraints, so it will be a Lagrange-Newton type method. Here I can just apply Newton's method for each value of mu, and then try adjusting mu and doing it all over again. Okay, yeah.
If you just take the dual of that, you get the same thing.
What's that?
So you did that to the primal and dual, the log barrier. If you do it to the primal, take the dual.
Take the dual of this, I'll get this.
You get the same thing.
Sure. Yeah, I mean these are closely related again. Yeah, in that kind of way. All right, so if I write down optimality conditions for this problem, I can just write down KKT conditions for this problem. for a fixed value of mu, I get these formulas that look exactly, in fact they are exactly the central path conditions, the primal-dual central path conditions, right? So this is strictly what they look like. These are just KKT conditions for this equality constrained problem. And now if I just define x to be the diagonal of the xi's as I did before, and then define the si's to be mu over xi, I get exactly this f of mu parameterized system of nonlinear equations. Okay? And so the concept of a central path, if you're dealing with primal or dual log barrier, you basically recover the central path that you get from the primal dual form. I can do exactly the same analysis by taking the optimum of the dual log barrier form. Okay? So the path following idea, let's talk about path following applied to the dual, because I think that's the framework that Aaron and Aleksander are going to be interested in. So the concept is just what I said. You just write down the dual log barrier. You at each value of mu, you take some Newton steps until you decide that you're close enough to a solution. Then you scale the mu by some factor, sigma, maybe make it adaptive if you like, less than 1, and then take Newton steps towards the new, for the new problem, the newly parameterized problem. Do the same thing on the primal, except here you have to take sort of Lagrange Newton steps because you want to stay feasible with respect to that constraint. So how do you get complexity results for this kind of approach? Well, you choose the sigma judiciously so that you only need to take one or a few Newton steps for each value of mu. Each time you decrease mu, you just take a couple of Newton steps. And therefore, the number of outer iterations, that by outer iteration I mean each decrease of mu, the number of decreases of mu you need to get a epsilon decrease in the duality gap is 1 minus sigma inverse log epsilon. So that's how you get your complexity. Okay, so let's look at, this is getting towards the end here, but let's look at what do Newton steps look like for when you apply them to the dual barrier. So let's go back to the dual barrier function, which was here, the unconstrained one.
Steve, are you going to talk about the complexity of these as well? The worst case complexity?
No, I'm going to leave the other guys to do that. Yeah.
Is it comparable to the Primal-Dual method?
Yeah, you can make it comparable. So if you look at the theory in Levin slides or Nesterov and Nemirovsky book and so on, it works with a more general form of this, and you can get these order square root of n type results there as well. But the n there gets transformed into some parameter of the barrier function. Here I'm dealing specifically with the log barrier. If you're dealing with other kinds of cones, you've got other barrier functions, and they come with other parameters that sort of govern the complexity. But you might hear more about that in the other talks. Okay, so let me unpack a bit. What does a Newton step look like when you do Newton steps on the dual barrier formulation? Well, if I go back to that dual barrier form and take a gradient and a Hessian, remember the Newton step is just the Hessian times step equals negative gradient. So the Hessian is just going to be a weighted sum of AI times AI transpose, where AIs are the columns of, the rows of the matrix A. And the gradient is just going to be 1 over mu times B plus the sum of, negative AI times 1 over these residuals. So anyway, I end up with this. That's the that's the gradient, that's the Hessian, and that's the step. Okay, so that's what a Newton step looks like for the dual log barrier. So that looks a lot like what I was writing down over here before when I took the primal-dual equations and compressed them all the way down. So in fact, you can get a little bit more precise about what the relationship is between the dual barrier step and the primal-dual step. So I'm going to go the other way. I'm going to take these dual Newton equations and unpack them into this kind of expanded form, where the delta z tilde, the dual barrier step, is one component of the solution of a kind of unpacked system. Okay, so to do the unpacking, I've got to define what is S. Well, that's easy. S is just the dual residuals. And I've got to define what X is. Well, I'm going to take X to be mu over the SI, okay, where mu is the current value of the barrier parameter. Okay? So with those substitutions, I can write out exactly what this system is. The AS term turns out, or AS inverse times E term turns out to be just a times x, which is equal to b. So I can, mash these two terms together and write them like that. And then if I unpack that a little bit, this is all just basic messing around on a sheet of paper with some linear algebra. I can show that the delta of z tilde is part of the solution of this system. Okay? And this is exactly the coefficient matrix that cropped up in the Primal-Dual setting. This is very much like the right-hand side that cropped up in the Primal-Dual setting. The first two components are 0, just like they were in the Primal-Dual system. Here they're 0 by design because of the way that I've defined x and s. But what about this last term? Well, let me remind you what the Primal-Dual system was. If you happen to be right on the central path, if you happen to actually be taking a step from right on the central path, then this x times s times z is just mu times e. Okay? And then I can do an apples to apples comparison between the step I get from the dual barrier and the Primal-Dual step. And you'll see that the only difference is in this last term. And if I compare the last term, the multiple here, in the case of dual barrier, it's just sigma minus 1 over sigma. And in the Primal-Dual case, it's sigma minus 1. So if the sigma is close to 1, remember sigma is a little bit less than 1. If it's close to 1, as it is in short step methods or Primal-Dual log barrier methods, then these two approaches are very much the same. Dual barrier is going to give you steps that look a lot like the dual component of a Primal-Dual method. However, if you're doing a long step method where the sigma can be quite a long way away from 1, it might be much closer to 0 than 1 in fact, then these two directions are quite different. But they're the same to within a scaling, okay? In fact, what happens is that in the case of sigma close to 1, as in a long step method, the directions are the same. It's just that the dual barrier is kind of overshooting. It's overshooting by amount that's by 1 over sigma essentially. Okay? So the two directions are the same, but modulo is scaling. So you can actually get, I wrote this paper with Yara in the late 90s that showed that you can basically get the dual barrier method to mimic what's going on in the Primal-Dual. Provided you solve the Primal-Dual equations pretty accurately for each value of mu, you get pretty close to the central path. You can take advantage of the fact that the dual barrier direction is kind of in the right direction. As long as you apply the scaling, you'll end up with a very good starting point for the next value of the dual parameter, which is sigma times mu. Okay, so you can sort of exploit the similarity between the Primal-Dual method and the dual barrier method. Okay, so that's all I wanted to say. I thought I'd leave off at that point because I think the other two speakers are going to focus more on the dual barrier setting, and they're also going to have more of the truth and beauty thing, which was sort of notably absent from my talk, which was kind of more elementary nitty-gritty tools. So any further questions?
Let's first thanks. In practice, how do barrier methods compare to Primal-Dual methods?
Yeah, I don't know, because in the LP and QP and LCP case, you only ever use Primal-Dual methods. Even the methods for nonlinear programming, they do have elements of barrier in them. They put the log barrier in, but then they also add these perverse truss regions that steer you away from the boundary. So they've kind of got elements of log barrier and Primal-Dual in a sense. That's the successful codes for nonlinear programming, like Nitro and IP-opt, sort of have that flavor. They're sort of Primal-Dual, but with barrier-ish elements as well. But certainly in the case of LP and QP, Primal-Dual is kind of, as far as I know, it's kind of the only game in town.
Is there any deeper reason why one always uses the log function and not just the sum of like 1 divided by the distances, 1 divided by the root of the distance?
Yeah, that comes up in that the log function has a self-concordance property that I think the other speakers might talk about, where the second derivative of the log function is 1 over x squared. The third derivative is 1 over x cubed. And so the third derivative is kind of the second derivative raised to a 3/2 power. So that relationship turns out to give you some kind of a bound on the part of the Taylor series that you're ignoring, and when you're formulating the Newton step. And that turns out to be critical in sort of being able to say that the Newton step is a good step, even if you're a long way from a solution. And that sort of property, that self-concordance property, shows up in other barrier functions for other cones, like the semi-definite cone or the second order cone. You get different functions, but they share that property. That's not shared by these other kind of ad hoc barriers.
So are there any implementations that doesn't use Newton method inside for solving? I know that Newton method solves these problem in few iterations.
Good question. Certainly, if you're doing the dual barrier formulation, you can use whatever you like to do the minimization, as long as it stays strictly feasible. I have seen some papers, like there was an early paper by Montero and co-authors for large-scale SDP, where they tried doing a log barrier on the SDP, where they used something other than the Newton method for the inner loop. I can't remember whether it was a coordinate descent or some sort of gradient. I think it maybe was just a steepest descent method. But I don't know of too much that uses the things that are... I mean, IPOP, the NLP codes use quasi-Newton approximations to the Hessians. So if you're doing true Lagrange-Newton, you'd use the second derivative, you'd use the Lagrangian of the Hessian, which would involve the Lagrangian of the objective and the constraints. But in practice, they tend to use finite differences or quasi-Newton approximations. So that's different, I guess. But it's still a Newton-like step.
Questions?
So when I've been talking to, some of the people who implement like IP solvers, they say that essentially, like for solving the first LP, the first initial relaxation, they'll need to use, they often use interior-point methods. But the moment you start adding cuts or branching or doing any of this stuff, they immediately switch to dual simplex. Because,
the reasons for that is it's hard to hot start interior-point methods. So if you're just solving one problem right off the bat, like a batch problem, then interior-point are often very competitive when you've got a large scale, when you're dealing with a large scale problem. But if you're modifying that by adding cuts or adding constraints or adding variables or whatever, it's hard to start to warm start interior-point methods. There has been work recently on making that a little bit better. I did some work in the early 2000s where we could sort of get a factor of 3 or 4 improvement from a hot start, but not the dramatic improvement that you get from simplex. Warm starting simplex from a feasible basis, or you can do really well. You can just take a few dual simplex steps and recover an optimal solution. But you can't get, in general, you can't get those kinds of economies with interior-point methods. Another setting that interior-point is really good at, by the way, is where the problem is very structured. So we had a lot of success in like control problems, MPC type problems, which are QPs where the Hessian is block diagonal and the constraint matrix is also block diagonal. So then when you write down these expanded big linear systems that you have to solve at every step, if you do an appropriate reordering of the rows and columns, you just end up with a block diagonal system, which you can solve in order n. So rather than order n cubed. And so that's used all through industry, and the MPC control industry uses that all the time. So it can take advantage in structures in ways that simplex sometimes cannot.
Any more questions? If not, we're going to come back in an hour and hear the more contemporary view of how these ideas are being applied in theoretical procedures. What? All right. Steve, you said... It took the whole hour, so it's fine.
I promised a long break, but there are too many questions.
So no long break, short break. Okay.